We're going to start by talking about the graph of a number to the x. So we're going to do 5 to the x. I'm going to tell you all the important things you need to have on your graph to get the points for this question. This will probably be a 3-mark question, and there's 3 specific things the examiner's looking for on your graph. First of all, to get the general idea about the shape of these numbers to the power of x's, so in our case 5 to the x, we're going to do a table of values. If you're not sure about how to draw a graph, I always recommend taking a few points. I've taken -3 to +3 and generating them into a table of values so you can plot a few points and get an idea about the shape. If you are super tech savvy, well, not even super savvy really, you can use your calculator and the mode function by pressing 3 here. So you could type in 5 to the power of x. Now to get the x, you need to press, where is it? Alpha and then x. And you could say start on -3, end on 3. And step 1 means you're going up in ones. So your calculator can also generate this table of values for you. Okay, so this is the x here, and the second one where it says f of x, it's the y. You can switch over to having it in fractions like that. I'm going to explain to you where these numbers come from and why the shape of the graph is as it is. You're going to need to know a little bit about negative indices. So say for example, our graph is y equals 5 to the x, okay? So here we would have 5, and we've said x is -3, so 5 to the -3. Now if you think back to indices, that's 1 over 5 cubed. Now those of you that know what 1 over 5 cubed those of you that know what 1 over 5 cubed is, that's 1 over 125. Similarly for 5 to the -2, that's the same as 1 over 5 squared, which is the same as 1 over 25. 5 to the -1 is 1 over 5. 5 to the 0 is what? What is it? Do you remember? 5 to the 0 is 1. Any number to the power of 0 is always 1. That's going to be important. So as your graph goes towards the left, so as the negative numbers go further away from 0, they're going to get smaller and smaller and smaller. So that means on the left-hand side of your graph is going to go like an aeroplane that's going to go to touchdown. But you're never going to actually get to 0. You're going to get smaller and smaller, but never crashing into the runway. Let's have a look what it's going to look like on the right side. So we'd have 5 to the 1, which is 5. 5 to the 2, which is 25. And 5 to the 3 is 100. 5 to the 3 is 125. So a couple important points. Your graph is never going to be a negative number, okay? That's why I haven't got any part of the y-axis below here. 5 to the x will always be a positive graph. Now, the things that they're looking for, the intercepts. We discussed here that the graph will get smaller and smaller and smaller, but it won't ever actually touch the x-axis or y equals to 0. It's going to go through this point here, which is 0, 1. I want you to label that. So I've labeled the asymptote. An asymptote is a line that the graph gets closer and closer and closer to, but doesn't actually touch it. So 1 point for the asymptote, 1 point for the intercept. There won't be any x-intercepts. The third point will probably be for the shape of the graph. Now we know that as the graph goes here to the left, it's getting smaller and smaller and smaller, or closer to 0. However, on the right-hand side, the graph is getting bigger and bigger and bigger, like 5, 25, 125. The next one will be 625. So you want to get the shape of your graph right. Okay, so you want to have on this side, you want to have it going down towards the x-axis, and this side you want to have it tending upwards, taking a really steep curve upwards. Let's have a look at a computer-generated version of the graph. Notice that this question usually comes up as sketch the graph. You don't need to get your ruler out and make millimeter by millimeter precisions, but you have to get the general shape right. So this is one that I generated using GeoGebra. Click like and comment below if you'd like me to tell you which apps that I find are really useful for A-level maths. GeoGebra, definitely super useful. Now, this is 5 to the x in the green. What about if we wanted to know what is 3 to the x? Okay, so this is going to be in blue now, and we're going to see what they have in common and what's different. So if you can see, the blue one here on the left-hand side is above, but on the right-hand side of the graph here, where the x is positive, 5 to the x is always going to be above 3 to the x. And let's think about why is that. If we had the same graph, if we had the same table of values, but we were looking at 3 to the x versus 5 to the x, let's think about what would happen. Here we would have 3 to the minus 3, which would be 1 over 27, 1 over 9, 1 over 3. 3 to the 0 would still be 1. That's why that's going to be a common point. If you look at your graph, both of them go through the intercept here at 0, 1. Because any number, if it's 3 or if it's 5, when you power it with 0, it will be 1. What else do we notice? Well, because 3 is a smaller number, these numbers over here are going to be smaller. That's why in our graph, 3 to the x is always going to be below 5 to the x. However, because it is smaller, when we invert it, when we put it 1 over 3 is obviously going to be bigger than 1 over 5. 1 over 9 is going to be bigger than 1 over 25. So the bigger number, so 5 to the x, will be on top of the graph for the positive numbers of x values, and it will be underneath the graph for the negative x values. Both of them, though, share the same shape, and they share the same intercept, and we could plot in here the asymptote. So both of them look like they're going to hit the x-axis, but if you zoom in enough, you can see that even when you get really big numbers, there's always a tiny little bit of space between the graphs and the x-axis. The last thing I wanted to show you was if you had 5 to the power of minus x, you can see that that's going to be a reflection of the 5 to the x in the y-axis. These are the mirror images of each other. We'll talk about that more later on when we do graph transformations. So, to summarize your graphs, 3 things that they want to see: the correct shape, the correct intercept, and the asymptote labeled. An asymptote is the line that the graph is moving towards but never will actually reach. Okay, so that's your graphs. Done. Finished. Okay, so for x to 2 decimal places, whenever we see in a question that it's going to be 2 decimal places, we know we're going to need a calculator. What I'm going to do is compose log on both sides. So say, for example, I put log base 5 on both sides. We remember from this rule previously that this x can come down and multiply. Log 5 has to be 1 because 5 to the 1 is 5. If these guys are matching, this is a quick little hint. If your base and your number here are matching, it's always going to be 1. So x is equal to log 5, 7. Now you may wonder how you're going to type that into a calculator. If you click this button here, this one here, and you want the 5 to be the base and the 7 to be inside the brackets, you're going to get x is equal to what we asked for, 2 decimal places, 1.21. So if you have an x in the power, you need to take logs on both sides so you can bring that x in front and solve the equation. In this situation, you're going to have the same method as the previous one. However, first you want to make this the subject. So what are we going to do? first we're going to move the plus 2 to the other side and make it a minus 2. So that's going to be 16. Now, I want to be really clear. I saw someone do this a couple days ago. Oh, well, this is the same as that. Those are not the same. And the reason is BIDMAS. You would always do the power before you would do the multiply. We're going to move the times by 4 to the other side, and it will become divide by 4. Okay, we're nearly at the place where we can take logs, but you don't want to be taking logs on a power x plus 1. You could, but you could also split it up here, like that. If you're wondering why you can do that, you've got to think back to your rules for indices, which says if these two numbers are being added together, you can split it up like that with the times in between. We're going to move the 3 to the 1 to the other side. And now I'm going to take log base 3 on both sides. You want the base to match the 3 because we've got 3 to the x. Bring the x in front. Log 3 is 1. And type this into the calculator. One tip is never to touch your calculator until you've written onto your page what you're going to type into your calculator. If you hadn't bothered to write this and you mess up when you're typing it into your calculator and your answer's wrong, you won't get any method marks. So always write everything on the page. You have to think, what does this look like? And this is actually a sneaky quadratic equation. What we're going to do is we're going to do a substitution. We're going to say let y equal to 5 to the x. You want to use y because you've already used the letter x here, okay? So now here, 5 to the 2x, you can think about it like this, 5 to the x squared. Or you can think about it as 5 to the x times 5 to the x, because you can split up 2x into x plus x. Whichever one of those you prefer, they're going to end up exactly the same in the end. So minus 2 times 5 to the x minus 35 equals to 0. Everywhere where I have a 5 to the x, I'm going to replace it with y. So y squared minus 2 again, y minus 35 equals to 0. I need to factorize. That's going to give two answers. Y equals to 7, y equals to minus 5. The urge now will be to stop because in IGCSE maths you're so used to finishing. But you got to remember that we said 5 to the x equals to 7 and 5 to the x equals to minus 5 because we said that y was 5 to the x. To solve these, we're going to take logs 5 on both sides. Let's start here. That's going to be 1. So here, oh, I forgot my log 5 over here. And over here. So that would be like this. This is going to bring us to an important point. If we try this, log 5 minus 5, you're going to get a math error. You're not allowed to have a minus in here inside the brackets. So I want you to eliminate this answer. This is going to be our only answer. You can. Depending on what the question says, you can type it in. This is another really sneaky question. I would recommend that whenever you see sums up here or numbers being added together, you break it down. So for example, straight away, I would change this into this. And the same here. Okay? So here, the 2x we can break down again because 2x is x plus x. 3 squared is 9. Okay, so this would be 3 to the x times 3 to the x times 3 to the 1 minus 3 to the x times 9 equals 12. This is looking super complicated, but you want to get rid of these powers up here. Whenever I see a 3 to the x, I'm going to replace that with a y. So I'm going to have y times 3 minus y times 9 equals 12. So that's going to give 3y squared minus 9y equals 12. You can see we've been given another super sneaky quadratic equation. I'm going to bring everything over to one side. And to make my life much easier, I'm going to divide by 3. Factorize. And I'm going to get 2 answers. Right, loop back. What did we say was y? Oh, we didn't write it down, but we had y was 3 to the x. This one we know is not going to fly. We know for 2 reasons. 1, when we take the logs, we get a minus in the bracket. And we know 2, because we just looked at the graph, and we talked about how the 3 to the x or the 5 to the x graphs, they don't have any negative y value. You see? Underneath the x-axis where y would be negative, it's nothing but empty space. So here we just got to take logs on both sides. Whenever you see an x in the power, I want you to take logs on both sides. Pop the x down. And that's 1. So x is equal to log 3, 4. Okay, I think that wraps Key Skill 5 up. Bit tricky, graphs, not super easy. I will see you in the next video. Bye for now.